All right, so chapter 12 is all about comparing multiple samples to each other. So you've taken two samples and you want to see are they the same? Do they come from the same underlying distribution? That's going to be the fancy idea. So let's talk about it. Yeah, so chapter 12 is the reading assignment, and let's talk about the first topic from it. So let's talk about A/B testing. Okay, so A/B testing is the idea of you've got some people and you've taken samples. You've got people in group A, you've got two separate groups of people, group A and group B, and you've taken the same data from both of them, and you've got some information. You've got some distributions of your data. You've got A, you've got B, and maybe A looks like this, I don't know, and B looks almost the same, like it's got a spike there, maybe it's a little more gradual in that direction, but maybe it looks a little bit like that instead. And now the question is, it kind of looks similar. Was the difference just randomness? So the question is, do these two pieces of data, these two sets of data from group A and from group B, do they come from the same distribution deep down? So are any of the differences just due to randomness, just due to chance? And A/B testing is the idea of doing this, of answering this question by doing some statistics. So let's learn how to do it. I have an unfortunate example. We've got some data from the real world. Somebody did a study back when this was unfortunately a thing. We've got a data set of mothers and the babies that were born to them, and we have some information on each of the mothers. So and the babies. So let me read in that table called baby.csv. I'll call it births. And so here's information about a mother and their child. So we've got the weight of the I think the baby probably in ounces or something. How long the mother was pregnant for before she gave birth. How old the mother was, how tall the mother was in inches, how heavy the mother weighed when she was pregnant, and then this last one is a bit unfortunate, but they took this data back in the day, whether or not the mom smoked during the pregnancy. All right, so whether or not the mom was a smoker, and that pretty clearly separates our data into two groups, right? We can take group A to be because it's a thing. If we didn't know it before, it is a thing, and we're going to discover it together. Babies weigh less if the mother smoked. That's an unfortunate fact. And so that's something that we're going to discover. So group A is going to be the weights of babies from the mothers who did not smoke during pregnancy. And so that's we'll see that group of babies is going to be a little bit heavier. We're going to prove that. And then group B is going to be the birth weights of the babies to the mothers who did smoke during pregnancy. All right, and so we're going to notice that there is a difference. Let's look at that difference, and then we're going to do some tests based on that. So let's see here. I might ask you to try this. So please get this table in, and let's talk about it a little bit. Let's select out just the things that we need from this table. First of all, births. Dot select. All we really care about was whether or not the mom was a smoker, maternal smoker, as well as birth weight. And that's all the data we really need. So let's call that something. We'll call that smoking and birth weight is that. And then how about I have you try something? Let's try to get some data on these on this information. Try to do the following. Here's a crushed dice for us. Explore the data. Here's what I'll have you try. Try to get the number of babies. Try to see what the data is like. How many babies had smoking moms and non-smoking moms? Get the number of babies born to mothers who smoked and mothers who did not smoke. And then 2, get the average birth weights of each group. So I think that'll probably end up being a dot group, right? So try to read in that table. try to get those average numbers. I'll pause for a minute, give you a head start. But that's useful. Let's explore that data together. Let's see how much data we have, and let's see if there is a real striking difference. And I'm assuming again that birth weight is in ounces for the babies. So yeah, give that a try. What's it called? So it'll be a couple dot groups. Try those.
Hi, Professor.
Hey, what's up?
We do have class today, right?
Yeah, we're doing we're trying something together right now. Give us a couple more minutes of a head start. We'll do one later. All right. So yeah, let's try this together. So I'll use the smoking and birth weight table that we made. And I think if we just do a dot group on this categorical variable, right, whether or not the mom smoked during pregnancy, unfortunate idea, but it looks like from this data set we have 715 mothers who did not smoke during pregnancy and 459 who did. So there's a decent amount of each. And if we want to get the average birth weight instead of just the count, because that's the only other column, we can do np.average. So we'll do it like that. Yeah, and so you can clearly see that about, I think it's in ounces again, there's about, on average, the babies weighed 10 ounces heavier to mothers who did not smoke during pregnancy. Crazy. So those are our two data sets. Let's look at the distribution as well. Let's take a look at the distribution. And our goal is to see how are they really different? That is our question right now. So let's do that. Dot where maternal smoker is true. This is all the babies born to smoking mothers, or mothers who smoked during pregnancy. And if we do a histogram on the birth weight column, that's that distribution of birth weight to mothers who smoked. And you can say the same one for false. And this is the distribution of weights to mothers who did not smoke. And so it does look a little bit different. It's kind of not very easy to see at the same time. So there is a cool thing that you can do. I don't think it's even in the documentation. But if you do a histogram and there's a couple different things that you could group by, the dot hist operation secretly takes something that you can group by. You can say group by the maternal smoker column, which is kind of neat because it'll show two distributions at once. So yeah, that's what you see. And I think that's all that I wanted to say. So you can see that there's kind of a clear difference. There's a bit, the birth for when smoker is true, the yellow one, it is a little bit more to the left. And so the question is that due to chance or not? All right, so that's what an A/B test is all about. So let's see. That's where we're going. So let's see. Yeah, so our goal is to ask the question, is that difference that we saw? Because the difference was decently large. We see that something's been shifted. The average is not the same, not very close. In theory, is the difference just due to chance alone? Because that's what gives us our null hypothesis. hypothesis, that's something that we can simulate, right? So for our null hypothesis, we take those birth weights and we try to assume that those distributions were exactly the same. The difference was just due to chance. The opposite of that would be our alternative hypothesis, where it wasn't just due to chance. There was something different. The babies really did way less when the mother smoked during pregnancy. So now our goal is, okay, how do we simulate this? How do we figure this out? What's the number that we're going to use to determine how close or how far away we were, especially these distributions, right? So I think a good statistic as we're doing our tests, the number that we can use is just like, as we're simulating babies, we can take their average birth weights, right? We can take their average birth weights for each of the groups. And the goal is, if the birth weights, like you subtract group B from group A with these groups in mind. And the idea is that group B, if the mother smoked, is supposed to be small, and group A is supposed to be a large number. And so we should expect to see, like, if there was no difference, we should expect to see the difference being 0, right? But if there really was a difference, kind of like we saw in real life, we should expect to see a negative number. All right, so negative values would favor, we say, the alternative hypothesis if we do our simulation. Okay, so now the question is, how in the world are we going to simulate babies and try to compare things? Because we have a data set of mothers and the birth weights of their babies. How do we simulate more babies being born? Like, how does that make any sense at all? So here's what we're going to do. Here's how we're going to simulate the null hypothesis. Because the idea was the distributions were secretly the same. There was no difference in the birth weights of the babies. It didn't matter if the mother smoked or didn't smoke. So with that in mind, here is the secret. Here's how we're going to do our simulation with our existing data. Because we can't go and get any more data, right? We can't just go ask, like, go wait 9 months, get some more mothers, right? It's not going to work. So we have to use the data that we have to do this kind of simulation. So here is the secret. Here's what we're going to do. The idea from the null hypothesis, the thing that we would like to simulate, is that there is no difference between smokers and non-smoking mothers. There is no difference in birth weights. In that case, these values that we saw for these mothers and these birth weight values, they didn't really depend on false or true here. If there was no difference, it didn't matter if there was a true or a false here. It's just like the weight was going to be whatever it was going to be. It wasn't affecting anything. That's kind of the idea. So if there isn't a difference between smokers and non-smokers, then shuffling the labels of who was smoking and who was not smoking shouldn't do anything to the answer. Does that kind of make sense? If that's true, then I can rearrange the labels. It doesn't matter. I should see the same kind of distribution. Okay, so if the null hypothesis is true, any rearrangement of the labels could have been equally likely. It did not matter if the mother smoked or didn't smoke. You do have to keep the same amounts. You can't just be like everybody in the data set smoked or something. You got to keep the same falses and true amounts to keep it like it was in real life, like we got the data set. And so yeah, our goal then to do our simulation to see if this was if we have firepower towards the alternative hypothesis is we're going to shuffle up all the group labels. Instead of false, false, true, maybe we'll put the true here. We'll say true, false, false or something. We're gonna shuffle all the group labels. Another word for shuffling is permuting, and so this test that we're about to do is called a permutation test. Okay, that's what we're about to do, and yeah, that's what's going to happen. And at that point, we've got a bunch of shuffled falses and trues, and we're just going to pretend that that's what really happened. And we're going to attach each of those to a birth weight, and we're going to find then for those new labels, we're going to pick the smoking mothers and the non-smoking mothers for those new shuffled labels, and we're going to get the average birth weights then and see the difference. And in theory, if there was no difference, we should see values very close to 0. Okay, so that's going to be how that works. Let's see, how do I want to do this? Do I want to do this now, or do I want to show you the next slide? No, I might as well kind of show it too. So here's a silly slide that I stole from the Berkeley people. Here's kind of what's about to happen when we do this kind of test. Like, here's maybe the original data. What we're going to do is we're going to shuffle who smoked and who didn't smoke. So instead of those labels, we're going to kind of turn it into those. Like, we're just going to shuffle them all around, because if there really wasn't a difference, which is what we're assuming under the null hypothesis, then it didn't matter whether the mother smoked or didn't smoke. Okay, so that's what's about to happen. We're going to assign new birth weights to different labels here, and that's our goal. That's what we're about to do. Let's make that happen. Yeah. Okay, so this is going to be important. These are the averages here. Boop. Let's call that the means table. And yeah, so this is the real life data. Again, the statistic that we're calculating is going to be we're going to subtract the weights of mothers who didn't smoke from the average weights of the mothers who did smoke. And so that's going to be the means themselves, right? Is means table column 1. That's the birth weight average. So I kind of want to subtract this from this. So do dot item 1 minus dot item 0, kind of. That's what I'm about to do. So let's call these are my means. And I want to take means dot item 1, that's this one, average birth weight of smoking mothers, subtract from that the average birth weight of non-smoking mothers. Means, that's just how we came up with, that's what we decided. Item 0. We could have done it in the other order, and then positive numbers would have told us something, told us the same thing. But this is the actual difference in weights that we saw in real life, and we're going to simulate numbers just like that again after shuffling. So this is observed difference. Okay, and we're going to have some simulated differences now. Okay. So here's the table. Here's what we've got, and so I want to shuffle these labels now. I want to shuffle those labels. One way to do it is to just like get these rows in a different order. We could take a sample of the whole table. So I could say smoking and birth weight dot sample. I want just as many, right? I want to put new falses and trues here, but I want just as many. So I want to shuffle every row. So sample how many? As many as there were, as many of these rows as there are. You can say dot num rows. And then I want to not duplicate anybody. Keep the same amounts of falses and trues so that I don't mess with anything. So I'll say with replacement equals false. And what this does is it gives me a new order of all the babies. But their birth weights are still tied to the same values, the same trues and falses. And so kind of what I want is just like take this new ordering of trues and falses only and attach it to the original table. Because then I will have shuffled the rows. Okay? That's kind of what I want to do. And so, yeah, if I take this then, if I do this kind of sampling, and then I get column 0, there's some shuffled trues and falses. So that kind of makes sense. I've got those things in a different order now. Shuffled trues and falses. And those labels I can reattach to the table. Shuffled labels is that. And then I want to take my original table, smoking and birth weight, and I want to attach those shuffle labels to it as a new column with column shuffled label and then shuffled labels. And so here, I've gotten a new true or false. I've reassigned these labels. I've shuffled them. We're going to attach those to those weights now. Because the idea is, under the null hypothesis, it did not matter if you smoked or didn't smoke. The difference was just due to chance. So in that case, these same values should give me a similar value, similar answer than compared to what we saw. Boop, just like that. So I'll call that original and shuffled. And what we want is to use shuffled label in birth weight rather than the original values. Because then we've got some new averages for new groups, right? So if we get just the shuffled people, we'll call it original and shuffled, just select out only the birth weight and the shuffled label. Just those guys. So this is like new falses and trues assigned to those weights. Let's get the average now, grouping by the shuffled label. Okay, that's what we want to do. So this is, we'll call this like shuffled only, is that. And then take shuffled only and group by that shuffled label, and then do the average of all those weights. That's what we end up with. So this is, once you've shuffled falses and trues, here is the new, pretending that nothing mattered, here's the new birth weight averages to mothers who did not smoke or shuffled labels and mothers who did smoke. And so there's still a difference because it's never perfect. But the idea is if the difference was just due to chance, the large difference that we saw in real life should eventually be simulated. Yeah, that's the goal. If it really was just due to chance, the large difference that we saw should be simulated eventually. Yeah, I think that is what I wanted to say. And so after doing this, I want to simulate my little statistic of the difference in those averages. So I need to like extract this column, get the dot items, do the subtraction all over again. So maybe we can make a function that does that for us. Let's call it difference of means, because that's kind of what we want, right? We want to do that grouping, take the average, do the differences. So you give me a table, call it table, and you give me a label for the group that you care about, like doing your differences of and doing your grouping by, because sometimes it was like shuffled label, sometimes the original one was maternal smoker, right? So we don't know the name of the group label just yet. So you give me that too. And so here's what we want. We would like to just get only the table with, let's see. Yeah, I guess I'll just type it out. We want that original table, so this is like our smoking table. We want to select out just the birth weight and the name of the group that we care about shuffling by, or doing our aggregation by at least. And so that will give me something like just this one. It's just like shuffled only. That's kind of the one that we did here. We selected out just the one with the shuffle label, but sometimes we wanted the maternal smoker, so we're keeping that a variable. So we get that. Let's call that that's my reduced table. And then I want to group by that. So I'll call it shuffle group means again. That's my reduced table, smaller, with just the two things I care about. Group by that, whatever label we were asking for. Sometimes it's shuffle label, sometimes it's something else. So I'll pass that along, and then take the average. And then the means, because what we wanted to do here was similar to this idea, right? Take the means, take the column one, do all those things. So yeah, means is that. It's shuffled group means now. Column one. So, and then it's observed difference that we saw here is item 1, item 0, and then we want to return that value. So this is just doing that kind of calculation for us. And so for our original value, what we did was we did that difference of means for the original table. We can do like, what was my original table? Or I guess we had original and shuffled together. We can pick out the one you care about right now. So if you wanted the original values, you can get past the maternal smoker column. That's why we made this group label a variable, like do maternal smoker column. That's just going to go by the original values, and here's my original difference. Or if you want to get the difference after you've shuffled, you can pass along the shuffled label. Because that was this one, our new categorization of all those, attach those to the weights now, and you had this kind of table. And so the difference is going to be these values. And so we're going to do a bunch of shufflings. We're going to get a bunch of values, and we're going to see how often do we see a value as extreme as the one as we saw in real life. Does that kind of make sense? It's similar to last chapter, but slightly different because we've got kind of two groups again, two groups going on here. All right, and so we need another function to do this and give me these values really quickly because we want to do that shuffling. So let's make another function. We'll call it def1 simulated difference of means. Okay, That's what I want. And so I want to make a bunch of shuffle labels. I want to attach them to the original table. I want to do this kind of difference of means. I want to keep on playing this game, shuffling these labels around, because if nothing mattered, if there was no difference, then this is what we saw. All right. Array of shuffled labels. So let's make that array of shuffled labels first. Here was this, right? Get my array of shuffled labels. So I'll take the sample, take that column. Then I want to attach these shuffled labels, to the original table. We called that original and shuffled right here. So I want to do that all over again. And this was the table with the birth weights and shuffled labels. And then I want to do a difference of means, because like I just made a table that looked like this. Use the shuffled label, do a difference of means, just like we did here. And that's one new simulation. And so return that answer back to me, please. Something like that. And so this is my simulation. So now I'm trading like which babies were born to smoking mothers and which ones were born to non-smoking mothers. And I'm getting this statistic back, that difference of average birth weights to mothers who smoked versus mothers who did not smoke. And we're just going to keep on doing that a bunch of times, because the goal is, we saw this value in real life. How often do we see that when we just shuffle the labels? Because if smoking didn't matter, then this should be easy to come by. Yeah, that's our p-value calculation. That's kind of where we're going with that. Are there any questions about that? Does that kind of make sense? So similar yet different to last chapter. Just like there's a concept of two separate groups of people. So yeah, that's what we're going to do. So let's just do a bunch of those. Let's get a bunch of differences. Let's do this 5,000 times because it's going to take a little bit. For I and NP at A range repetitions. And so what I want to do is just like do a simulation. Get me one simulated difference of means here, and append that to my existing differences array. Oops. And shove that right back into the differences array. Differences equals that. And once that's done, I've just got a bunch of differences of means there that have been simulated under the assumption of the null hypothesis that there was no difference between mothers who smoked and mothers who didn't smoke. So we shuffled those labels, pretending that didn't matter. And this is why I only did 5,000 instead of 10,000, because this one takes a while to do a shuffling. That one, that's a pretty involved process. And so that's taken up a lot of time right now inside of my computer. But while it's thinking, I do have a question for you. I'd like you to try all this. I'll give you all this code after it's completed. But I think the goal now would be, all right, we've got all these differences. Let's do a histogram, because the goal is to see like how many times do we see something this extreme or more, right? Because negative values, we said that negative values are going to be in favor of our alternative hypothesis. How often do we see a negative value, especially one that's as small as this one? Yeah, that's our. And by the way, we called that observed difference. We can compare against that as well. Oh wow, it's still going. Let's see. Well, hopefully I typed it right. There we go. All right, so let me give you this. Your computer is probably more powerful anyway. Let me give you all this code, and at least think about how you could do like a histogram, stuff like that. So if you go to the code from class page, you should have everything that we've done so far. And so now what I'd like you to try is at least think about how you'd write this code. It might take a while to do the same kind of simulation if you run all these cells, but try to generate a histogram, or at least type out, knowing that it's called differences. Well, how would you make a histogram of these differences that we've simulated and compare that histogram to our observed difference value that was like -9 or whatever. And also, with that in mind, you can make a p-value, generate a p-value if you can. It might take a while for you to create that differences value if you have to run that cell yourself, but at least think about how you would create that histogram, like what would be the code that you write out to make a histogram and generate a p-value based on their observed difference value. Yeah. Okay, let me try now. So with these differences, we can put them into a table, right? We got to put them into a table to make a histogram. Difference between, and I'll call this difference between group means, because that's the value we're getting back. And I'll shove differences in there. And I'll do just like a standard histogram, all right? So that's that one. And just for fun, let's give it a title. It's this PLT thing that gives it a title. If you remember that, give it a nice little title, PLT.title. Just make a fancy graph just like you do in real life. Prediction under the null hypothesis. So assuming the null hypothesis is true, this is what we get. And I can also print out our observed difference, just for fun. Print our observed difference is the following. It was -9 point whatever. And these are all the values that we generated, we simulated, assuming that we could shuffle the labels and there was no difference. How often did we see a value that was -9? That's way off this graph, right? Never. Never. And so that is our p-value that we got by doing simulations. We call it an empirical value because we got it through that. So if we do our differences, we take our differences values and we see like how often was it equal to our observed difference, or was it even more extreme, so even more negative, less than or equal to. How often did this happen? So np.count on 0. That. And like 0 times. To get a percentage, of course, you divide by like your repetitions, how big the thing is, but it's still 0%. So that's our empirical p-value. How often did we simulate a value as extreme as we saw in real life? Never. if you do in billions of simulations, eventually this will give you something, but it does not now. So that's kind of how that works. And that leads us then to the idea that our alternative hypothesis was probably the right one. So probably the mothers who smoked, they really did way less on average. We did not see, our null hypothesis did not predict the extreme value that we saw in real life. Okay, does that kind of make sense? Because that's what we did. Any questions about that? So that's how that worked. Let's see here. Yeah, I think that's most of what I wanted to say. So let's just review, because that was quite involved, I think. So we had two groups, right? Group A and Group B. We're like, here are the distributions of Group A and Group B. Smoking mothers and non-smoking mothers for their birth weights. It looks like there's a difference. We take averages and subtract, like there is a difference. That could be our statistic then. And all right, the question is, what were those distributions really not the same? So could the difference then be due to just chance? Because that would mean that they were secretly the same. Your null hypothesis is usually something that you can simulate, right? It's like, okay, they really were the same. There was no difference in the population. The distributions of those weights were exactly the same. Any difference that we saw was due to chance. So that was that null hypothesis. And then the alternative is just the opposite of that. Like, okay, there was a real difference. It wasn't due to just chance. The number that we'll use as we're simulating is just something we make up. We did differences of averages for each of the groups. But as long as you're doing something with each of the values of the groups, you're making some number that you can compare against, that's fine. And so that's what you get there. That's what's happening. And yeah, I think that's all that I wanted to say. So to simulate, right, for this specific problem, we're like, okay, under the null hypothesis assumption, it did not matter who smoked or who did not smoke. And so that means if I shuffle the trues and falses and try to do the same kind of calculation, I should get the same value, right? That's what the null hypothesis is implying. We saw that that's not what happened, but that's what it's implying. And so, yeah, that's how that works. And yeah, I think that's most of what I wanted to say about all of that. So we shuffled the labels. That's how we did every simulation. What we did was we shuffled the labels, attached them to new birth weights, and calculated our statistic all over again. We saw what we got. How often did we see what? So like we took some labels, we shuffled the labels, and we did our calculation. And so yeah, every time we got a new difference of means. It was a very involved function, but we were able to do that every time we did the shuffling, and we're able to do that a bunch of times by like tacking on all the things that we did and working together. So yeah, I think that's most of it. We got a bunch of little differences that we simulated, our little statistic, and yeah, I think that is everything. I think that is legitimately everything that we talked about. So we got a distribution of our statistic, and we saw that the value that we saw in real life was nowhere on that distribution. So that goes to show that it's very, very hard to simulate that under the assumption that the null hypothesis is true, which gives us reason to conclude that the null hypothesis is not worth believing. So that is, yeah, that's kind of how that all worked out. So it's very similar to last chapter, just we had two categories, okay? Two groups of people. Cool. I think that's what I wanted to say. So yeah, questions about how we did all that? Does it make enough sense? So you read about this, but this is a start. We've done a bunch of different kinds of hypothesis tests now, and so I just want to give you like 2 slides of like a little cheat sheet of what we've done, right? So let's try to remember our examples from before, because this is last chapter too, and let's try to think about like how this all fits together, because we're asking a question, we want to know a yes or no answer, usually with a p-value, like, okay, if it's small, then we'll conclude one thing versus another. And so let's think about all the things that we've seen. So one of the first ones from last chapters we just took one sample of a bunch of things, and there were 2 different categories in that sample, that one sample that we took. So we had like flowers that were purple and flowers that were white, okay? And our question was, like, what was the actual proportion? What was the actual proportion that we saw? So we came up with a number that we could simulate, right? The null hypothesis was, okay, it was like a perfect 75-25 split. And so the statistic that we're going to simulate could be a number of things. It's like, all right, the proportion of purple that we saw, that was the thing that we simulated. You could also have done some sort of like how far away was what we saw in our simulated purple flower proportion. How far away was that from our thought that it was exactly 75%? That would be like a subtraction in absolute value. And then the way that we simulated our garden was we planted just as many flowers, and we used our assumption from the null hypothesis like it really was a 75-25 split. So that's kind of how that one worked. You just come up with a number and you simulate. Okay, you got 2 categories for your one sample. We also had, you took one sample, you had a bunch more categories than 2. That was the jury panel stuff, right? Like the ethnicity distribution for Alameda counties. Like you had like 4 or 5 different ethnicity groups, and you wanted to like compare them all against each other. And so that one, the way that you come up with one number that shows you the difference between those groups. One of the ways to do that was the total variation distance, I think. Yeah, either difference or distance. It's been a chapter. So TVD for short. We did that, and we compared what we got when we simulated with what we assumed it should have been, right? We always assume what it should have been, and that's the number that we can then simulate. We can keep on simulating that. So that was like... we had a bunch of different groups, like our observed distances, like for these all different values for all these different ethnicities, right? And then our null distribution was like, okay, these were the values that we saw in real life, or these were the values that it was supposed to have been. How far off was it? Was it really drawn from that distribution? And so, again, we use sample proportions because it can take a big, long distribution with more than one thing in it. And that was how we tested that hypothesis. How often did we see a value that we saw in real life or more extreme? Okay, so that was the first one. And then, so that was a bunch of categorical stuff, kind of. We got a bunch of categories with one sample. You've also got one sample, and you've got a bunch of numerical data, right? That's another way that you can test hypotheses, like, okay, what was something true about this numerical data, like the scores in that midterm section, that sample class from the last chapter, the midterm data example. So our question was like, okay, was something wrong with that section 3 of people? Okay, was something wrong with section 3? Was something off? And so to simulate, what we did is we kind of shuffled labels, technically. We wanted to know, like, okay, the average of, we made a bunch of new section 3s. And so our test statistic, when we're simulating new section 3 scores, is we could just take the average again. Or you can take the average and like how far away was it from what we expected it to be, like the original one. We expected it to be what we saw in real life, for example. It's like you don't have to always pick the same number. It's just as long as you're consistent and as long as you can compare it. So could have been just a mean value. Could have been a difference of means, a distance of means, whatever you wanted to do. But the way that we simulated our one sample numerical data and trying to figure out our answer, like, was there something off about section 3, or was it just drawn from chance? We took a sample of just as many people in section 3. We simulated another section 3, right, with replacement equals false. And so that's what we did. That's what happened. And that's how that worked. Yeah, I think that's what I wanted to say. Yeah, and so that's all last chapter stuff. Questions about those? Does that kind of make sense, all those differences? That's stuff that we've done. It's just all on one page now. And yeah, the last one is the new stuff. So we've technically got 2 numerical samples. That's what we had today. Even though it was in one data set, we really had 2 numerical samples. We had one group of smoking mothers and one group of non-smoking mothers. And we were trying to figure out, did those samples come from the same distribution? Okay, that's what happened. That's what we were trying to figure out. And yeah, so what we did is we shuffled, right? The way that we simulated values is we shuffled. We took our original data, we took a sample with replacement equals false of just as many things, right? Of just as many things. And we tried to notice, was there a difference in those groups even after that kind of shuffling, right? So you could have, our statistic could have just as easily been like subtract group B from group A or group A from group B. It didn't matter. It really didn't matter, okay? So there's those, and yeah, you could have also just done a distance calculation with an absolute value. Either way, as long as you're consistent and you know which direction points you towards your alternative hypothesis, okay? That's how that works. That's how that happens, okay? And so that's the one that we just did. And so they're all slightly different, yet still similar, okay? And I think that is what I wanted to show you. So you can come back to these as you're trying to study, maybe. Questions about those? So I don't think I have much more. I don't know if I want to go back to code today, but I want to talk just about what it means, like causation stuff. Because we've got a p-value, right? We got a p-value, like it was 0% chance, right? A 0% chance that we saw a value as extreme as we saw in real life. 0% chance that our model would predict the value that we saw, the stark difference that we saw. 0% chance. And so that causes us to, we say, reject our null hypothesis in favor of the alternative. But now the question is, was smoking really the problem? Right, now we're trying to determine causation. So what, was smoking really the cause of that weight difference? Or was there something else? Was there another confounding variable that is the true case, right? It's like, I don't know, smoking makes you not want to eat, maybe, right? It keeps you feeling full. I think I remember reading that once upon a time. I don't know if that's true, actually, but like that kind of makes sense. Like that maybe it was the lack of hunger or something in the mother. Like, was it really the cause, though? I guess that caused the other thing, so it didn't really matter. But was there something else? Is there some, like, maybe smoking mothers tend to be less educated, tend to be maybe slightly make less money, and so it's harder for them to, like, I don't know, eat as well as non-smoking mothers on average. Like there's things that you could imagine that are going on here, right? So was smoking the cause of the weight difference? That is what you're asking right now. And so, or was there some other thing that was secretly the problem? All right. And so the answer right now is we don't know. Like we are forced to conclude that there is a difference, right? We're forced to conclude that there is legitimately a difference between smoking mothers and non-smoking mothers in terms of birth weight, but we can't say that smoking was the cause because we didn't do a randomized experiment, right? We didn't do one of those. What would that have implied, right? The only way that we could do like a randomized controlled experiment is the fancy term, right? Would be to like have some pregnant women and tell them to smoke or to not smoke during their pregnancy. Do you know how unethical that would be? That would be horrible. You can't do that. You can't just ask people to smoke or not smoke as they're pregnant. So all that we've done is we've got a sample of convenience, kind of, if you remember that word. So that's all we have right now. And so we've shown that there's an association between smoking and birth weight, an association going on there. But we can't show causation because there may be factors at play here. Like maybe all the smoking women had something in common and all the non-smoking women had something in common as well. Okay. If you want to like average out all the differences, you would have had to do a randomized controlled experiment where you told just random people that were pregnant to smoke or to not smoke, because then there really would be, all the differences would be averaged out. That would be wrong, though. That would be ethically wrong. You can't do that for this example. So you just kind of got to keep your sample of convenience, but you can't conclude anything strong. So yeah, that's what I wanted to say. So that's in general, you can only really conclude causation when you've got a randomized controlled experiment going on where you've got like a control group, a group that's like not smoking, and a treatment group, a group that is smoking, and you've controlled who is in which group. All right. So if you select, right, if you got your treatment groups and your control groups at random, like you're talking about like a shot or something like a vaccine, that's the graph I've got on the next slide, for example. If your treatment and control groups are taken randomly, if they're selected at random, then you can conclude causation, right? That's what they do in drug trials. They try to average away the differences in people so that there is no difference in the groups of people who got the drug, did not get the drug, and so they can see how effective it was really, because there was no difference at that point. So we cannot conclude anything other than association for example today, but if we did a randomized controlled experiment, we could have concluded causation. That's the moral of the story. Does that make sense? That's what's going on there. And yeah, here's a fun graph. I might have already shown this to you, but the idea was they wanted to prove that this was the Moderna COVID vaccine. They wanted to prove that it was working, and so they legitimately did, right? Or before they gave it to everybody, they did a randomized controlled experiment. They wanted to make sure they got two groups of people, right, randomized. They gave one group of people the actual shot. They gave another group of people a placebo shot, which did not have the vaccine in it, but they thought they got the shot, right? And then they kept track of those two groups over time. Blue was the placebo, red was the people who got the shot. And you could see that, and then on this axis is how frequently they got COVID. And so you can see that the placebo shot people just kept spiking up and up because the COVID was spreading. And then the people down here, they were not getting infected. Okay. And so you do that test, right? You can see that there's a difference, right? In like their average rates of getting COVID. You can conclude something. You can conclude that the vaccine was working because of that difference. All right, because there was a randomized controlled experiment going on. Okay. Any questions about that? So that's how you can conclude those things. So yeah, I think that is most of what I wanted to say. Let's do one more slide for fun, and then I think that's a good place to stop. So, okay. Again, you really, if you can do it, and as you're doing a trial, you want a randomized controlled experiment. You want to randomize things, all right? Because otherwise, you can only show association. You have no clue if there's some confounding variables, confounding factors at play here. You have no clue what's going on, and that's a problem. Okay. Yeah, I think let's talk about this slide. So here is a silly study that they did a while ago, but it's still true. So you got people who own iPhones, you got people who own Android phones, right? And so you've got people buying apps on both of the stores. Like you got the App Store and the Play Store together, and look at what happened. It looks like the conclusion of this chart was that Apple users were more willing to pay for apps. Do you see that the share of the amount of people spending money, or dark blue is the Apple App Store, the amount of people spending money on apps is more for iPhone users than for Android users, all right? Whereas Android users, it's gaining traction, but they're not paying as much for their apps. So it looks like the iPhone users are paying for their apps at a rate that's more than Android users. All right, so that's what they found. And how they get this data? They did a survey, right? They asked people, all right, what kind of phone do you own? Did you buy? Which apps have you bought for your phone so far? How much did you spend? Something like that. That's so that they did a survey. And the question that you might want to ask, does owning an iPhone cause you to spend more money on apps? There's a causation question deep down there if you want to learn about that, you want to think about it. Who knows? The question is, who knows? We can't tell from this graph. We cannot tell from the study, even though it looks like for sure, owning an iPhone, you're spending a lot more money than Android users. We can't tell that having an iPhone causes that, though. I hope you can imagine. Because you're just asking people who already had the thing whether they spent money or not. You're not controlling, right? You're not just giving somebody an Android phone versus randomly assigning somebody an Android phone versus an iPhone and telling them to go use it and try to download apps, all right? That would be the only way you can conclude causation, right? If you gave random people random phones and people are just going to buy what they want, though, right? Because and so this is just an association again. It's not a causation because you know that there's probably other factors at play, right? People trying to buy stuff. In general, I think that iPhones are a bit more expensive than Android phones. And so there's an income difference, right, in the people who own iPhones a lot of the time. Also, there's a geography difference. again, due to income. Like certain countries are going to be more likely to have Android phones than iPhones because the GDP of that country is not as high. There's not a lot of purchasing power for whatever their currency is. Like iPhones are generally more expensive, and so people already have money in the first place when you've got an iPhone, and so they're more willing to buy apps. But again, you can't conclude causation. There's just an association going on. You have no clue if just like owning an iPhone makes you spend money. It could just be that the people who own iPhones, they happen to have more money on average than Android users. Something like that. So that kind of makes sense. So that's why you need randomness. Otherwise, you can just all you can show is association. You cannot show causation unless you did a randomized controlled experiment, because then there really is no difference between the groups. But right now, there is a difference, most likely. Okay? So I think that's what I wanted to say. Any questions about any of that? That's the moral of that story, and this is where I stopped last time. So I landed a little bit earlier today, but time for you to work on stuff. So, to be continued. Da-da-da. So yeah, if we're good, let's check and make sure there's nothing else to do. We'll finish up these slides next time. We'll give us some opportunities to try out this process ourselves with two separate groups of people doing an A/B test. But for now, I think that's all that I want. So no, we haven't finished the slides, so no new assignments or anything to talk about. But we will continue with this next time, and I think that's all that I wanted to say.